All right, students, for video D, we're going to talk about two other ways that Mr. Otten does clamping, but kind of a different way of doing clamping than we often think of doing. And then we're also going to look at the ways that he joins his fixtures together. So here we go, let's get to it. Okay, this is a grilling flat top, and so you can see here is the rim around the flat top, and then there's a giant piece that would go in here that is the actual grilling surface or flat top surface. And you can see that there are some clamps over here on the sides that are both holding the sides in place, but will also hold that flat top at the right location. You can also see that there are these devices, and these are giant magnets, so electromagnets that can be used to position the top in place. And in fact, when the top is put in, you can see it's being brought in on a chain hoist with a magnet holding it, and then it will be held in location while the welding happens. There we go, there's welding happening on this. And it is held in place by the magnets. You can see that it's on the rotary table. The entire fixture can lean to one side, and that gives the robot access down there where it needs to go for welding. So magnets are another way to do things, so long as you have a part that's magnetic. And so that doesn't count for any of the stainless steel parts or any of the aluminum parts. Well, some stainless steel can be magnetic, but not many stainless steels are. And then it's great for the steel and the iron containing parts. Okay, so magnets are one way to do it, but that's not the only way that things can be done. A lot of times things can be held in place with suction cups, and so Mr. Otten loves to use suction cups on things. You can see there are several different kinds of suction cups here. Here's a big purple one. This is, you can see it's about 2 inches in diameter here, and it is what we call a double bevel, or a double bellow, sorry. It has this edge right here, and then there's another fold right down here. That means that it can fold together and collapse more than some others. Here is a black one, so that's made of a different material. It is also a double bellow, and you can see it's got a big range of motion. And then this one is a single bellow, and it does not have nearly the amount of motion that the others do as far as compensating for either warps in the material or displacement of the material. Now, when you want to use vacuum cups, one of the things you have to do is be really careful to think of these not as locators, but as clamps. They are pulling clamps rather than pushing clamps, but they are clamps. And so you need to have something like this, where this suction cup is pulling the material down, but this bar is acting as a locator to set the position to be correct so that the part can be welded. The suction cups just have too much deflection possibilities. Some of them have a surface down in them that looks like it's rigid and is made for to be a locator, but you cannot tell when you put something on here if it got drawn all the way against that locator or not. And so you always need to put a locating surface next to a suction cup if you're going to use suction to hold something on. And you want it to be fairly close to each other, because if I put this suction cup a long way from the surface, then it will take that sheet metal and it will bend it over on the suction cup portion around the locator. So, some other things that you need if you're using suction cups. You need vacuum. So you can use a vacuum pump, but vacuum pumps are expensive to maintain. And so a better way to do that is to use a little device like this. This is a vacuum generator. So the way that this works is you blow compressed air in here. There is a venturi, that is an area where the air goes from a large size flow path down to a very skinny flow path. And as it goes to the skinny flow path, it has to accelerate. And as it accelerates, the pressure will drop by, and so when the pressure drops, you can then put a little tap on the side of that area. And because the pressure is lower there, that counts as vacuum. So you would tie that lower pressure area to this line. Now this is going to exhaust all of that compressed air out of the end here, and that's kind of loud, and it uses a lot of compressed air, so it's kind of expensive. Compressed air is a pretty big cost in a shop because compressors are not very efficient. And so when you are using these little vacuum generators, you typically need to put a muffler on the output so that they don't spit things into people's eyes. And it may require that the workers then wear hearing protection when they're using this fixture. But the reason that you use this rather than a vacuum pump is that this is, these are generally $50 to $150, depending on what kind of volume and what kind of vacuum they can draw. And a vacuum pump will be thousands of dollars with hundreds of dollars of maintenance every year to replace all the seals. Okay, so we have vacuum. How much vacuum can we get? How much holding power can we get from one of these? Well, the maximum amount of vacuum that you can draw, if I draw all of the air out from the inside of this suction cup, then it is atmospheric pressure that is holding the item onto this suction cup. And so atmospheric pressure at sea level, you can get a maximum of 1 atmosphere. So that's 14.7 psi. That's the maximum. And as you go to higher altitudes, there's less atmospheric pressure. And on some days, there's less atmospheric pressure. I guess some days can have more if there's a big high pressure system in the area. So what do you do about that? Well, you never count on more than 14 psi. To get to those higher vacuum levels requires a set of really sophisticated turbo pumps and things that are extremely expensive. So, you know, you might consider 14 psi to be your max. I would sure go more conservative than that and count on the maximum being 12 or 10 psi being the maximum vacuum that I could draw. And what might affect that? Well, if I'm using a rough surface, then it's not going to seal as well against the suction cup. And, you know, if it is a non-machine surface, and so maybe there's going to be a little leakage, I might err on the side of 10 psi or something. So once you have that number, that like if we assume 10 psi, then you take the radius of this suction cup and the cross section, or the area here, the projected area is pi r squared. And so I take, and that's going to be in square inches, so pi r squared square inches times 10 pounds per square inch will give me the number of pounds of holding force that this suction cup can generate. And so a larger suction cup generates a whole lot more suction force than a little suction cup. And so if you can do it, you want a large suction cup. Some other things that you have to think about, though, is that these, you know, these are bought to be relatively heat tolerant. There are some cheaper suction cups that are not heat tolerant at all. But even so, this is still a plastic or a rubber, and so material, and so it definitely has to not be right next to where you're welding. These materials will wear out both from ultraviolet and from heat, and so typically you try to put them a little further away from the welding process to protect them. Okay, I think it's really informative to look at the way that he made things as well, the way that he holds things together. And so when you look at this, he tries to do really simple machining. So you can see that this riser block down here, this riser block is to get the suction cup at the right height, rather than machining pieces that would be more complicated, he just uses a little piece of 1/2-inch thick material that he had, puts 2 holes in it so he can screw it down, and then 2 more holes in it so he can screw down a piece of angle bracket. And this is just an extruded angle bracket that he can get. It has some slots here so that he can adjust the height of this relative to the locating block that we have down there, because you might need to change that a little bit to make sure that the part will get drawn down fully. And then he has a place to mount the suction cup. Some of these other suction cups have a neat capability. This one has a very large range over which you can adjust its length. Now notice this suction cup does not have a locator next to it, so to really be usable, this is just a demo he made for us. To really be usable, you would need to have a locator nearby. And see how he's put adjustability into things. He's put some slots here so that he can adjust the position and angle of this suction cup relatively easily. And then over here, he's made a little block. He makes a bunch of these little blocks to act as a mount for the suction cup, and then also as an air manifold. The air goes in here, and then where the vacuum comes into here and then into the suction cup. And then each of these little manifolds that he makes, he just puts on some threaded holes down here, and he can change the length of all of these standoffs, and it makes a really simple system for putting things together. The way that things fit together is a little hard to do with this camera, but anyway, with this kind of extrusion is you use these T-nuts that slide down inside, and you bolt down into those T-nuts, and that's how you hold something in one of the channels of the extrusion. But how do you hold extrusion pieces together? Well, sometimes he will use these cast objects that you can buy from the companies that make this material. And so that's a really good way to strengthen a corner a lot. One problem is that the 8020 or Bosch Rexroth is not all that expensive, but every component that you buy for it is super expensive. That's where they make all of their money, is on all of these little doodads that hold things together. So if you can make your own holding together components, you can save a lot of money by doing that. And so sometimes he will do something like this, but another alternative is he has these plates and he just stamps these out. He's got a lot of metalworking machinery there because they make ovens all the time, and this is just scrap metal from some of the pizza ovens that they've made. And so he just shears these out, and you can see it just has the corners sheared off to make it a little bit easier to use. It has the T-nuts underneath, and he bolts that in. But he doesn't think that that is enough to keep corners really good. So if we look down in here, he has also threaded into the center core of this piece and put in a screw that has a relatively big head on it, so that he has it bolted here as well as the backup up here. That required him to drill a hole all the way through so that he could put a wrench in there to drive that screw in. But he likes to do things on those two different levels just to make sure that they're really solid and held in there. If you make a fixture and then the fixture loosens up and it's wobbling all over and you make a bunch of bad parts, that's really bad. So that is the way that he puts things together, and that's all going to be really useful to you because you're going to be creating a welding fixture, and that welding fixture is going to be made of extrusion. You're going to be putting on whatever you decide to hold the parts in place, whether it be like toggle clamps or suction cups or magnets, whatever seems to be the right solution for that time, and then building up this whole fixture to be able to provide access so that the welder can come in and weld on the different features that are in that part. So, hope you found this interesting. I think it's always neat to see not only the way that the book talks about things being done, but seeing how people actually implement it in industry and how they use commonly available materials to make the fixture inexpensive but really hold the parts well. One of the questions that people have asked him before is, how do you decide when you're going to use pistons as opposed to the manual clamps? And his answer to that is that he uses the manual clamps anywhere he can because they're cheaper. So where can you use them? Well, you can use them on the outside of a part. But anything that's up underneath inside a part, he doesn't want the operator have to get up under the table to do a manual clamp. And so inside the part, he will use pistons to move things in place. If he has a fixture that gets used often enough, then he might put pistons on the outside as well, or if it has to have a lot of locations just so the operators can use it more quickly. But that really increases the cost of the fixture a lot. So whenever he can, he uses manual clamps. All right, looking forward to seeing you in class so we can practice some of this and talk about the project. Bye.